Bueno, empezamos, recuperamos las jornadas. Sí. Perdón que lo analicé un segundo, pero igual voy la dejo. Irina va a presentar a Nicolas Kaufmann, que lo tengo con Irina. Te lo quería presentar.
Nicolas is coming from Bern. He's from Switzerland and he's doing his PhD at the University of Bern. He came to do a short visit a month here to work with our group, Grupo de Astrofísica Planetaria, and he's working in planetesimal fragmentation applied to planet formation. So he's going to talk about this work that's been doing recently.
Thanks for the introduction, Irina. So today I'm going to present a bit of my work, but also part of what the rest of the group does a bit. Otherwise, my project doesn't really make sense without the context. So as we start with every planet formation or exoplanet talk, we start with our favorite pictures, the newest updates from the exoplanets.org archive with all the known exoplanets along with their detection methods. So, not good. Okay, we're back. Good. So as we can see, we got basically four major, we know about 5,500 and how much? And 14 exoplanets at the moment confirmed by various different detection methods. And we got four major categories, let's say. We got the hot Jupiters, so very massive planets that are close into their star. Basically, the period is a proxy for the distance to the star in this case. And you can see that orbital periods of 1 day. So those are very short and very massive. So the hot Jupiters, then we have the cold Jupiters, which are more analog to the ones we actually see in our, the giant planets we see in our own solar system, the low mass planets that are close in, and the distant super Jupiters. You might ask, well, this does not look any way, shape, or form like our solar system, and there's should be a huge gap. And you can see that that is due to an observational bias, since most planets are detected by radial velocity and transits, which are very much sensitive to close-in high-mass planets due to how the detection methods work. However, we not only see planets, we can not only portray them as such, but we also know of systems as a whole. So at least half of the planets, I think, yes, are in multi-planet systems, so where we observe multiple planets at once. And as we can see, they, on a system level, we can see quite similar sizes and masses for the planets, which is a phenomenon called peas in a pod. But also across system, we can see quite different properties that the systems have. So for any planet formation simulations, it is quite a challenge of how to reproduce planets, because on an individual level, we know quite little about all the planets we observe. So we basically know the mass and the radius, and even those to a quite bad precision. And also, we need to have a theory that is able to explain how we get to form such different systems that are yet then similar within themselves. And it's also hard to find, to actually quantify what is the ground truth of what the planets are in all systems, because we suffer from detection biases that are hard to account for. Since you've seen, we have 6 different methods that are all slightly have slightly different sensitivities in quantities that they observe. And so this slide is going to be slightly dense. So we start with a theoretical model that basically go through the processes we know or think we know are involved in planet formation. So we start at time 0 with star formation, but for us guys, we don't know too much about that. Second thing, if you have any questions, you can ask them during the talk. I like to be interrupted since I tend to forget to mention some things. And if you're confused and get lost, just yell at me. So yes, time 0 star formation has a huge influence on planet formation, but we usually don't model that, and we basically assume that the star is already formed. Where we start is with the disks, and we can see here these beautiful ALMA images. And as we can already see, we have one of the major challenges of planet formation is that we have a huge diversity in the disks we observe. And as such, it makes it quite tough to, so we get quite a lot of different initial conditions that we already have to use for our planet formation simulation. And depending on where we start with our simulations, this can have a huge influence, and this is quite hard to quantify in terms of what is our time 0. So then from here on out, we have the first formation stage during the lifetime of these protoplanetary disks. These tend to dissipate on the time scale of maximum 10-ish million years. And so what the first stage is to grow a planet is we start with the dust and the pebbles. So these are micrometer to centimeter sized objects. That's actually what we get to observe. We're not actually observing the gas disk, but the dust. And that's the first stage. As you can imagine, growing from these small centimeter-sized to planet-sized objects is quite tough to modulate, to model, and to describe with a theory, since we're climbing many orders of magnitude and time, going from short growth timescales of 10 to the 4 years to then giga years for the actual ages of certain planetary systems. So from these dust particles, on the other hand, we also have on the bottom panel, we'll see sort of the interactions with the gas disk. And on the top side, we see what with the solids happens in these disks and how we get to grow the solid component. And towards the right, it will be time, but also size as we progress in time. Then the next step in question is planetesimals. So as we see asteroids in the solar system as the remnants of these primordial bodies, we get to grow 100 meter to 100 kilometer sized objects called planetesimals, which are the basic building blocks from which we then grow through mutual collisions the cores of planets. This has to happen during the during the lifetime of the gas disk, because we know that when we form giant planets, that these have to accrete gas, and so the gas disk has to be present. So this puts a sharp constraint on the formation timescales of these so-called protoplanets that grow through the collisions of these planetesimals, we believe. For the dust and pebbles, these experience radial drift due to the headwind of the gas disk, since it's partially pressure supported. And then also on the size scales of protoplanets, we get radial movement, but due to a different effect, which we call orbital migration, which you will see the effect of in our simulations later on in the movies, and which also leads to inwards movement of these protoplanets on quite short timescales, depending on the mass. From there on, we have to grow the giant planets within the lifetime of the gas disk. And this happens by accreting once these protoplanets become massive enough, they can bind a part of the gas disk gravitationally and form giant planets. This is a very simplified picture and is very messy. So yeah, the gas accretion, as mentioned before, to then form these giant planets, which has to happen in the lifetime of the gas disk. And this is sort of the standard scenario that we call core accretion, which is sort of the way we started thinking about planet formation, giant planet formation. And then for the inner planets, we get longer timescales where we can grow them after the lifetime of the gas disk, since they have quite a slower envelope and get created through the collisions of many such protoplanetary embryos. And then that's how we get to form the inner giant, the inner terrestrial low mass planets. And then we also have to check for, because after we formed them, we have many of these planets, and then we have to dynamically evolve them and see if the systems are actually in stable configurations to then come back to what we actually observe. And so you can see that basically the only actual images on this plot are the actual observations, let's call them, are the protoplanetary disks and the actual planets of the solar system / the exoplanets. So we can see that we have to have models that encompass quite a large time frame and size scale that we basically got no observational evidence for, apart from a very few exceptions of, for example, PDS-70c, where we actually can observe a forming planet, but these observations are quite rare and few and far between. Yes. And also, not only do we have to, sorry, I should have put this on first, not only do we have to evolve them dynamically, but we also have to evolve them thermodynamically and see how the composition evolves. For example, if by irradiation of the star, we get to lose the envelope or the contraction and stuff like that, that matters on longer time scales than the actual formations. And you can see that sort of here we're on a giga-year time scale for these processes, and for these we're on 10 million years time scale, which makes it quite challenging to model all these things at the same time. And it even gets messier because, especially in the regime of the solid growth from the dust to these planetary embryos, there has been a lot of development in, let's say, stepping stones and ladders. For example, by the direct collapse of dust and pebbles, how big these bound objects then actually can be. Are these directly protoplanets or are they planetesimals? So we can have a few orders of size that, depending on which simulations / which physical processes we invoke, that these solids can be bound to. Or we can bypass the whole thing, and there's also a second theory of how we form the giant planets, where the gas disk itself becomes unstable at a certain point, leading to the fragmentation of the gas disk, which is a totally different process. So it is a very messy picture, you can see. And from there, how do you make sense all of this? We have many individual processes, the orbital migration, the growth of solids. And what we then want to have is an end-to-end formation and evolution model, since the only constraints we have from observations are the disks at the beginning and the exoplanetary systems at the end. And so how do we do this? To account for the different initial conditions, we have to translate the observations into initial conditions that we randomly vary. And then we have to run this with a global model to then produce final systems. And then what we can do is we can compare these to the actual observed population of exoplanets. We can't compare this really on a system-to-system level since the data is so bad. And then what we can do is we do statistical comparisons, for example, frequencies, how well do we match the current rates, for example, hot Jupiters, which is around 1%, or how many giant planets do we have on average form per system. And then we can go back and either have, say, either rematch, and we can make predictions, for example, because we can cover parts of the parameter space that is not covered by observations. For example, we can predict planets in the zones where we're not sensitive yet, which can inform what future instruments we want to create and things like that. But also, on the other hand, if we don't match and we see an issue, we have to go back and improve our individual models. And that was, I'm sorry, that's what a bit we're talking about today. So the planetesimal fragmentation will be a process that we were looking at in my work that we had to improve, since the model we had for the basics, the planetesimal disk was a bit simple, and we had to improve that. And so this will be my part of the work, whereas the rest is sort of the framework that we use as a whole group.
Nicolas?
Yes.
It's just a question, maybe the rest of you that more very simple, but maybe not very easy to answer. How well are because clearly in order to compare your models to, and make some fittings with the observations, you need to take into account the observational bias.
Yes.
So how well are those characters?
The observational biases are very hard to characterize.
So
but what you can do, and what's the most favorite, is you take the big surveys, for example, Kepler or the big R-Bay surveys, and these have, so the individual surveys have quite well constrained observational biases.
okay.
And then you compare them to the subset. You almost never compare it in a statistical sense to the whole population, as we've seen from the exoplanet archive, because there it's very hard to quantify.
So in order to, let's say, to find like a perfect fit, you have to do it separately for each of the, and then somehow you weight on this independently.
No, you compare it to individual surveys. It's basically
that's what I mean.
try
But
to do.
in the end, you have to get, let's say, your best fit model. So you have to take into account all the surveys somehow.
Yes, in theory, but it is more about, the tests are quite simple that we use. It's, for example, frequencies, and it's not like density maps where you really can. It is rather on a discrete level, or the number of the multiplicity of giant planets is something that we can very well compare. And we're not at the stage yet with precision that we can really. It is more, it's already a challenge to have a model that fits, that produces all kinds of planets in, let's say, approximately the right frequencies and radii, rather than actually having a best fit model per se. Yes, so this is the approach of population synthesis. That's what we do in Bern, and we work with and all our populations, synthetic populations that we create and compare, are available online to toy around with. It's quite interesting to see, and they're quite useful if you want to, as an observer, have a theoretical background of what you want to observe. So this, as you've seen with the many physical processes that are involved, this also calls for a formation model that has all these processes included. And this is the Bern model, which we lovingly call the beast. And so basically, we model the formation of planets in two stages. We have the formation stage, that basically covers the first two panels, and then an evolution stage, because you can see the timescale of 10 gigayears would be very unfeasible to happen, and we know that planet formation also has to happen on a short timescale. And so we have two parts to the code, the formation and the evolution, which basically encompasses simplified models that we abstract from more complex simulations for each of the processes that we discussed before in the planet formation study. And then we can actually look at how this looks when we actually simulate a synthetic planet population. So we have the same diagram as we had in the beginning. This time the period is replaced by semi-major axis, but that's just a scaling thing. Mass, and as you will see, and these are the solar system planets, just as a reference. And as you can see, once we start the movie, bada bing, bada boom. Yes. And so here we get to see the evolution over time for 1,000 systems to create a synthetic population of exoplanets. Yes, in each disk we have to put 100 of these protoplanetary embryos on which we then get to accrete these planetesimals. And this is basically the sum total, the total of all the planets we have. And the Monte Carlo variables, as I mentioned, so to account for the different disks in the beginning, are basically the gas mass, the size, and the solid mass in these gas disks. And then we get to create this synthetic population, which roughly matches the, there it goes again. And here you can nicely see the migration of the planet that is strongest around their Earth masses that I talked about before. That's why they move inwards. And then we get to, and this is how it looks at the end, and we can see that we are able to roughly reproduce the planets, the different types of planets that I mentioned in the beginning. So we have the cold Jupiters, we have the close-in low-mass planets that are either dry or wet, depending on where they form. So basically, due to the temperature fall-off in the gas disk, water is either in its solid or in the gas form, depending on how far we are from the star. The further away, outside of what we call the ice line, is in the solid form, and the blue dots refer to the planets that have more than 1% in volatiles, or mostly, which is mostly water ice. And then we have the inner dry planets that have less than 1%. And so these two make up the close-in low-mass planets that you see in the observational side. And then we also form a few distant super Jupiters, and basically the gap that we've also seen between the low mass and gas planets. But we are unable to reproduce the close-in hot Jupiters, but this is also a bit due to a detection bias. As said, they were on an occurrence rate about 1%, which is not displayed in the diagram you see. So this is basically the baseline case. This is how our planet formation simulations work that we do in Bern. And then we come to my part of the work. So, yes, we also get, that's the beautiful thing, obviously, about our simulations, that we also get to predict parts of the parameter space that are not well probed by observations or not probed at all. And so we get to make predictions how, if the same principles apply for the inner planets, we get to extend and make predictions for these parts. So then we come to my part of the work. So basically, so far, we considered only planetesimals of a fixed size. But when we have these embryos and planets in the disk, they increase the random velocities of these planetesimals, which leads to collisions among them. And when these collide and the high energies are high enough, they get to shatter and they change size and produce fragments, illustrated by this nice picture here. And depending on the size, they will experience radial drift, which then changes the structure of the solid disk quite a bit and the accretion onto the core. You might ask, okay, yeah, you changed radial structure a bit and the size, but why does this actually matter? So if we simulate the formation of a giant planet, we can see on the left-hand side formation tracks for the same initial conditions, but only varying the size of planetesimals. This is without fragmentation at the moment, but for different sizes. But that's basically what we do when we introduce fragmentation. We start producing planetesimals of different sizes, so to speak. And as you can see, depending on the size we choose, so this is the mass over time of the same planet. Ignore the different dashed lines for the moment. That's a different way we calculate the random velocities, which are also very important, but that's a bit too out of scope for the moment. So you can see that depending on the size, we end up with very different types of planets that are very vary by basically 5 orders of magnitude in final mass. And so this is basically due to the accretion timescales that have to be different before we can accrete the gas in a runaway form. And as you can see, for bigger planetesimals, it's harder to grow so for the biggest planetesimals, the 100-kilometer one, it's basically almost impossible to grow giant planets, since their accretion timescales are quite a bit more. And not only that, but the picture gets even messier when we look at where these planets end up in the disk. So not only has it a huge influence on the final mass, but also where they end up in terms of distance to the star. So for example, if we, for the very low mass planets, they migrate significantly less than these high mass planets. And some of them, depending on the size, even get lost to the star when we have marked X, they fall into the star. So they might even get lost. And in the model, this looks like this. So we have the planetary embryos that accrete the planetesimals, and they're increasing the random velocities, and the planetesimals increase their own random velocities due to their gravitational encounters. And basically what we added to it is now we allow collisions between these planetesimals and fragments that are just smaller sizes of planetesimals that we start to introduce. And this basically then should give us, if we go back to the last slide, this lets us investigate if even with bigger planetesimals, which we believe to be from a planetesimal formation standpoint, which we believe to be the ground truth at the moment, if we get to still grow giant planets with bigger planetesimals when they're allowed to collide with one another, if that changes that whole paradigm. So that was the sort of interest we had. Yes, and so now what we did is we ran a 1,000 system, a little parameter study of big planetesimals and small planetesimals, once for the case as we have before, so basically where they don't get to collide at all, once where we say, okay, once they collide and the collisions become energetic enough, we transfer the mass to planetesimals of a size 100 meters, and once with a dynamic size where they basically, depending on the energy of the collision, the size of the fragments we produce gets smaller and smaller. And as we can see, this is sort of the expected case. For smaller planetesimals, we get more massive planets. So this is the ground case. This is sort of on a population level what we've seen for the growth tracks before. But then also, once we start introducing fragmentation, we can actually see that this really is the case. So once we introduce fragmentation, reducing the typical size, we start to produce giant planets for the kilometer size. Once we start introducing fragmentation for the kilometer-sized planetism, we actually get to form giant planets, whereas this is not the case for the 100-kilometer ones. However, if we start introducing smaller fragments in the dynamical size case, we actually don't get to form them again, and this is due to the intricate balance between smaller planetesimals, smaller sizes of solids being easier to accrete, but they also deplete because they move inwards due to the radial drift, as I explained 2 slides before. Since I'm a bit short on time, I will skip this slide here. And basically, we can see this in a disk where we basically, so what we do here, we did a little study where we basically put the planetary embryos at different points in the disk. So these are 100 different systems that are evolved separately. And what we can do is we can do this So without fragmentation and with fragmentation, and as you can basically see, we get enhanced growth. But not only that, but also because of the radial drift of these smaller fragments, we get to form icy planets that come from quite a bit further into the disk, and they also grow more massive. So we can see that it makes a big deal of change, especially for the icy planets in the outer disk. This has 2 reasons. A, because icy planetesimals are easier to fragment, so we produce more of these. So obviously we expect a bigger effect, but also because these get then to drift inwards and accrete the drifting fragments. And we can do this not only, this was all with single embryos in the disk, but we can also do this as for the nominal population with entire systems. And as we can see, the picture remains largely the same. We get enhanced growth, especially in the outer disk, leading to these migrating icy planets. And we also get to form 100 giant planets, some giant planets with 100-kilometer planetesimals. So we can say that we sort of saved, or at least reduced, the problem we have with core accretion to reproduce the entire population of exoplanets. But this is a quite simplified model, and sort of what is the next step and why am I here? So the next idea would be, since we expect the outcome of collisions between planetesimals not to be one single fixed size, but rather a size distribution, we want to implement that next, that we get to fully resolve the size distribution and describe the solid disk more accurately. And this we can see here as a comparison with a more sophisticated model that Irina works on. We can see that if we start introducing that, it is quite important to have the typical size of these planetesimals, of these fragments, to properly describe the typical size, and that the size distribution actually might lie in between our different descriptions that we've used in the paper. So what are the takeaway messages? Fragmentation has a huge effect on planet formation. It benefits depending on the size we assign to these fragments, or how we describe this fragmentation, or what the collisional outcome is. It can have a benefiting effect or a hindering effect to form giant planets, and mostly it is relevant for the planets in the outer disk. However, there's some caveats. We're very dependent on how we describe how easily these planetesimals are fragmented into smaller pieces. And also what happens at the inner disk edge is a bit hard to model at the moment, since these smaller fragments then drift inwards to the inner disk. And this was my talk. That is 45 minutes on the nose. Yes. Do you have any questions? Thanks very much.
Preguntas, comentarios.
Maybe just Nicolas, you can comment how much time and what computer do you need to run this kind of population synthesis?
So the biggest time constraint.
Just because here in the institute, we mentioned what they need to run the simulation science.
So the limiting factor is the actual, when we go back to the so when we go back to all the physics, so the limiting time is the n-body interactions between these embryos. These are actually modeled as discrete bodies. To integrate those, depending on how many we have, that is sort of if we only have one embryo per disk, they're quite fast to run. So we obviously have to, for each system, we have to use a CPU core, which is a separate instance to run it. So running 1,000 systems, and now we even have bigger populations that we want to use, since another PhD of ours is working on machine learning descriptions and comparisons. So we need a bigger data set, and there we actually have up to, I think, populations with 20,000 systems. So that's 20,000 instances, CPU cores that you have to run it on. So that's one constraint. And the actual time per simulation that runs can be up to a few weeks, depending on how many embryos we put in the disk for the n-body integrator, since that goes as n squared. And those are the main two factors when it comes to computation.
2 weeks running in which computer?
Running in our cluster, we have an HPC only for our group, which is equipped with new EPIC Ryzen. I don't know how to. Yes, that's a few weeks.
It's a cluster only for your group?
Yes. What did I want to mention? Yes. Yeah, so also a few weeks. Yeah, depending on also how long we do the n-body integration for. Because we had the second project where because as you've seen in the, I'm hopping all over the place here. So for terrestrial planet formation, we believe the formation timescales to be a bit longer, to also encompass this giant impact phase when the gas disk is gone. We have to integrate the n-body longer, and these take quite a long time, so a few months. There we go up to, I think the longest we did is 200 million years of n-body integration, which then takes quite a long time. But yes, yeah. Does that make sense?
But those you don't do population synthesis with. those
Yes.
ones, yeah, also with the long.
Yes.
Oh.
But the spread of so the thing is you have quite a huge spread depending on what system you form on the computation time, because if all the limiting time scale for the n-body integrator is the orbital period of the closest in planet to resolve that, and so if you have close-in planets, it can take quite long, or many close encounters, whereas other systems, depending on where we put the initial embryos, it can happen that they're quite quick. But obviously, if you want to properly compare, right, that you don't have a bias towards longer, you have to wait until all the simulation finish, or otherwise you're introducing a bias. And usually it happens that we like 10% of the systems run for significant long. Okay. Yes.
¿Algún otro comentario? Juan, y en el chat no hay nada. Bueno, le agradecemos nuevamente, Nicolás.